Hi, welcome to Neuroverse, a podcast hosted by Carolina
and Clara, where we discuss all matters from neuroscience to philosophy and beyond.
Today's episode is on designing generative models. And to help us with this topic, we're joined with Pierre Glaser, a PhD student in machine learning at the Gatsby Computational Neuroscience Unit in UCL SWC. Pierre is working with Professor Arthur Gretton on advancing the methodology of flexible generative modeling. Previously, Pierre was a software engineer at INRIA, where he worked on improving the performance of distributed scientific computing in Python. Thanks for joining us, Pierre.
Thank you for having me.
Thank you for joining us today.
So to start us off, what is a generative model?
Okay, so that's a great question. And I think generative models have been just like without me starting to define it, I think it's been the object that has been one of the most central focus points in the machine learning community over the last like 10, 20 years, and even actually earlier than that, because they were even central to more traditional statistic communities. The general idea is that if you're a practitioner or if you're just a person that's working with some data, and that setting is all the more frequent, that access to data has been vastly democratized over the last decades with the advance of new recording technologies and with the increase in compute power. We are now faced with tons and tons and tons of data. And a very natural question to ask if you're trying to understand the data is what is the process that generated that data? Okay, and the ultimate thing for a statistician would be to have access to an object, something that is usable, that could encapsulate exactly the generative process that created that data. And if you have access to such an object, then you could, for example, query it to generate new data, which would be a very simple query. So you could ask that object, oh, can you generate a new data point for me? And that would be very useful, for example, if you're a person that wants to, for example, generate new images. And if you have access to a generative model of images, right, you could then generate easily new images by asking the model to generate some image. Of course, if you just ask the model to generate an image, it's not necessarily going to generate the image you have in mind. So in general, the queries to this model can be a bit more complex than that. Mm-hmm. So typically, you could ask a model to generate an image of a dog. Okay, and so all of this formalism of querying a model is very well encapsulating by the concept of sampling from a probability distribution. And so I think the most easy way to describe what a generative model is that is simply a probability distribution that represents the generative process that generated the data. And once you have access to this conditional probability distribution, then in the language of the queries that I've discussed before, generating just a new sample is just sampling from this probability distribution. And querying slightly more complex queries, like, for example, generate an image of a dog, can be seen as conditional sampling of the rest of an output given an input. So, for example, if the generative model is able to generate pairs of description and images, then you could ask the model to generate a sample from the conditional distribution of the image given a specific text. And that's a more elaborate queries that is well formalized by the concept of probability distribution. So I would say that, yeah, deep down, a generative model is just an approximation that is usable of the generative process that created some data of interest.
Okay, so you feed to the model data, and then it learns the data, and then there's a probability distribution that when you query it, so when you like ask it a question, there's an output like of the most appropriate in regards to the question of the probability distribution.
So there are a lot of things to unpack. So maybe the first thing to unpack right now is right now I've just said that indeed a generative model is, so for the sake of maybe this discussion, we're going to restrict it to just being a probability distribution. I haven't told you whether or not all probability distribution were valid generative models. And for sure, you could imagine that plenty of generative model, if you just assume that any probability distribution is going to be a generative model, you're going to see that clearly some probability distribution are better model than others for some given data sets. Some probability distribution just fit the data better than some others. So typically, for example, just a Bernoulli distribution, which is a distribution that returns randomly either 0 or 1, is not a right model for images, because images are a much more complex object than just like a single value that's either 0 or 1. So typically, there are a lot of constraints on models that makes model valid and even good models for a given data set. In practice, the way models are chosen are by maximizing some kind of goodness of fit criterion. Okay, and so that's exactly what you kind of alluded to when you said, oh, you fit a model to the data. So you're going to start with a set of candidates model. Okay, this can be either very large or smaller, and we can discuss it a little bit after. And then you're going to find among this set of candidates which model fits the best the data. And by that, I mean which model maximizes a goodness of fit criterion that tells you, okay, this model reasonably well the data. Okay. So that maybe was the first question, the first thing I wanted to unpack.
Yes, thank you.
So when you're judging how good of a fit the model is that purely based on the output? Is that like how well the output matches what you wanted to output to begin with?
So that's again like something that deserves a lot of time in order to be unpacked properly. So I guess by output, you refer to the output of the model. And that, in a sense, even is something that I have not properly defined in that discussion. So it's itself like something that is a bit ambiguous right now. So we could either refer to the output of the model as possible result of queries. So, for example, samples from the probability distribution that the model represents. Okay. Or it could be actually something else. Like, for example, let's say you have a model that is just, I'm going to go back to this very simple example, this example of just a Bernoulli distribution. So you have a model that represents a probability distribution whose sample can either take two values, so either 1 or 0. Okay, so it's like a coin toss, heads or tails, for example. Okay, you can imagine that it's the output of the model can either be, for example, samples from this model, so heads or tails or 0 or 1s, but it can be also, for example, the value of the probability that the samples take, the value 1 or the value 0. And typically your head or tail like probability is not necessarily even. It can be also slightly unbalanced. So for example, the probability that the output or that a sample is 1 could be 0.7 or 0.8 or 0.9, or it could be 0.1 or 0.2 or something. So the concept of output could either be the probability of a given output or a proper sample. It really depends. And in practice, the way a model is fit, there are various ways you can fit a model that either depend on samples from the model, so outputs probably in the way that you meant originally, but you can also fit model by evaluating the probability of your dataset and maximizing this probability. And this is actually a very fundamental concept in statistics, which is that you should somehow select the model that assigns the highest probability of realization of the data that you have at hand.
I am still a bit confused about the two different types of output you can have. So one is about the most appropriate statistical tests you can do on the data and whether you can fit the model to the data. And then the other is about the query.
I guess the point I was making is that we could see in the framework I've posed at the beginning, I've discussed about this concept of queries of the model. And you can see sampling from the model as a query, but there is also a very important query, which is evaluating the probability that the model assigns to a specific realization. And that's another query in a sense. And so when we think about the output of a model, we can think about the output of any queries. And so we have to be a little bit more precise if we want to formalize exactly what an output means. That's maybe what I meant.
That makes sense. But the only thing I don't understand is I thought that since the model is probabilistic or it's statistical, that the model itself is the probability of getting a certain output. But now you're saying that the output is the probability of getting an output.
No, that's a very good point. So when you think about, for example, I'm going to come back to this example because it's simple, but yet it has enough, I guess, like subtleties so that we can solve some of the misunderstandings. So typically, if we look at this Bernoulli model that is a model that represents a random variable that can either take value 1 or value 0. Okay, the model should represent both of the probabilities of the associated to each event. So both the event that the variable is going to take value 1 or the probability that the variable is going to take the value 0. Okay, so it represents the two at the same time, actually. And then a query could be, give me the probability that this realization in particular happens.
Oh, okay.
Okay, that could be a query.
Interesting. And then related to the model itself, so like you mentioned this example, but you said you choose a generative model that exists. So do all these models already exist and you just apply one to your data, or do you actually create a model?
Yes. So I guess there is a philosophical question behind whether or not they exist, and I will skip that. I guess the thing I want to focus on, maybe the way usually we create a family of model is by what is a process that is referred to as parametrization. So let's come back to that coin toss example or that Bernoulli example. Okay, we could consider, so each model in a sense is represented by a unique single value. That is the probability that the output of the model is, or that the sample, that the random sample that is represented by the distribution of the model is either 1 or 0. So typically, let's say it's 1. Then let's say the probability that the value that the sample of the model will be 1. Then also the probability that it's 0, because it's just 1 minus the probability that it's 1, because those are the two possible only realization. So it's either 1 or 0. So if the probability that the value is 1 is 0.7, then the probability that the value is 0 is just 1 minus 0.7 is 0.3. Okay. And so in a sense, each of this model is represented by a single value, which is the probability that a variable is 1. Does that make sense?
Yes.
Then you can create a family of model by allowing this parameter that represents the model to vary continuously, for example. So you could, ask yourself the question, can I somehow fit a model, okay, among a set of candidates that is the set of all Bernoulli distribution with parameter P, where P varies between 0 and 1. Okay, and the framework of optimization allows you to select the best model among all, and there are infinity of models within that family, right? Because P, this parameter representing the model, varies continuously between 0 and 1. So there are uncountable number of models within that family. And yet the beautiful domain of optimization and statistics, this intersection, really allows you to find the model that best fits the data if you're using, for example, a maximum likelihood criterion. Does that help?
Yeah, no, that makes sense. So I like this simple binary coin toss example, but you mentioned images and generating an image when you ask your model to say, like, create an image of a dog. So in that case, what goes in?
Yes. So in a sense, what goes in when you ask generate an image of a dog is going to be pretty much like of a dog, right? You're asking the model to generate an image of a dog. So you're going to give as input to the model the fact that you want an image of a dog. So typically you're going to give somehow this text, a representation of the text dog. Okay. And then on these models, usually the idea is that those models are trained, for example, on a joint description of an image and of an image itself. And so then if a model just sees a lot of pairs of description of image, image, description of image, image, it's going to understand the sense of the words and their relationship to the value of the pixel in each image. Okay. And so provided that the model understood this relationship, then it's relatively simple to ask a model to do conditional sampling. So to ask a model, okay, conditionally on the fact that I want image that are related to this description, and this description is a dog, generate images that are related to this description. And the process of getting the structure of the model is much more complex than just a Bernoulli distribution. A Bernoulli distribution, in a sense, can't be that complex, although to be fair, it could, coming back to that example, so if we were, for example, trying to generate a coin toss, the value of this parameter P could be the result of a complicated transformation of the input. So for example, let's say you wanted to generate coin tosses, right? Like realization of coin tosses, but with different probability depending on the value of the input. So the input could be either dog or cat or something. And for each of these, for example, categories, you might want, it's a very convoluted example that doesn't have real life application, but yeah, I'm just using it for the sake of the simplicity of the presentation. You could, want to draw samples with different probability of the sample being 1, depending on the category you give as input. And so in a sense, like, this parameter P that represents the model could be a complicated function of the input. Well, here it's going to be the same thing, right? In generative modeling for images, the parameter representing the generative model are going to be complicated functions of the input. And from the input to the generative model, once you have mapped this input to a generative model, then you can somehow query this generative model. And this itself is an entire field. But you can find ways to create this generative model to create images. Does that make sense?
Yeah.
I now just wanted to ask, so in terms of more like real life applications, I'm aware that like ChatGPT and Dall-E use generative models, right? Could you explain a little bit?
Yeah. I just wanted to come back to something that you said quite early in the presentation, which is, so there was this, you mentioned like fitting a model.
Yeah.
And then you mentioned generating data that are the most representative of the input or something like that, right?
I asked, like, according to the probability distribution, does it then extract or the most appropriate answer?
Yes, no, that's actually a very good point.
Yeah.
So this I just want to clarify, but essentially you don't want to create the one that's just the most representative.
Okay.
You want to be diverse, in a sense. So you want to generate data that's more representative more often. So the data that's less representative less often, but you still want to generate data that's less representative sometimes.
Okay.
Otherwise, you're gonna be biased towards high likelihood sample in a sense. Does that make sense?
Yeah, but the feeding of the data, does it start from there that you don't always add in like the most accurate, the most pretty data? You also include data that's maybe not super representative so that then the output also isn't biased in that way?
Yeah, essentially the ultimate goal for the model is to replicate well the data distribution it was given to as input. So if the data that it was given to as input is very narrow, the model should output a very narrow scope of data. If the data is very wide, the model should return a very wide range of data, right? What it must not do is finding the data that is the most probable and return it all the time, because that would necessarily narrow the range. Whatever the range is as input, it would necessarily narrow it in its output. And that is problematic because at the end of the day, our ultimate goal in generative modeling is just a perfect replication of the input data, if that makes sense.
Yeah, that makes sense.
Okay, cool.
Yeah.
Your goal is a perfect
replication of the process, of the generative process that generated your input data in the first place. Your like training data, essentially.
Okay, so this is really interesting, but just so we can have a bit of a better idea, can you expand a bit on the applications of generative models? So I'm aware that ChatGPT and Dall-E, they use generative models, or they are generative models. Could you talk a bit about that?
Yes, yeah. So I guess I don't know what else much to say about ChatGPT or Dall-E, that they are precisely generative model of both, text and description samples in the case of Dall-E, or ChatGPT just of plain text. Essentially, there are generative models of this kind of data, and they've been fit on enormous amount of data, which allow them to be extremely accurate and precise in their representation, and which have, as some people would argue, even emerged to some specific skills within those models that we didn't think were possible in the first place, like things very close to reasoning.
Yes, but these skills that we didn't even think could exist, such as reasoning, like you said, is this because of they processed the data and they fitted the model exceptionally well, or is there something else going on? And I also wanted to add a follow-up. Why do generative models have such an amazing capability, such as ChatGPT? Why not other types of models, such as discriminative models or reinforcement learning or unsupervised learning or deep learning models? So what is so unique about generative models?
So yeah, there are plenty of things. Maybe the first comment about reflection. So I think capacities of whether or not generative models are thinking, quote unquote, in any sense. I think we just need to be humble in that discussion, because this is a discussion where that's extremely controversial these days. Like, a lot of people are not agreeing at all, even among the most famous figures in the AI community. So I wouldn't dare to say that I know, but I would just encourage people to realize that all those models are, especially ChatGPT, most language models are trained by predicting the next token in a sentence. So think about it, just predicting the next word in a sentence, right? And if you think about what you do when you talk to people, how often have you tried to complete the sentence of someone when they were talking?
Yeah, very often.
I'll just leave it as that. I think like we have to be humble in this kind of discussion, because like I do think that there are a lot of similarities between the way language model work and the way the brain works, that one being a specific example, but you could find others. And so thinking that they're either completely quote unquote dumb machine, or that, of course they're not perfect, but I don't think that to this day we can assert with high certainty that they're just like, basic matrix multiplication objects. And that's what I would just say. Regarding why there are kind of more, I guess, like performance than other kind of model, as you mentioned, for example, reinforcement learning model. I'm not sure whether or not, in a sense, they are more performant. So there are a couple of aspects to that question. The first, I guess, aspect is just that the output of language models is language, and the quality of the output is can be judged by pretty much everyone, right? And I think judging the quality of the output of a reinforcement learning model is a bit more complex, right? It's a bit more application specific. And so I do think that one of the reasons why ChatGPT is seen as more performant is just because I think it just reached more people and gained more popularity. Another thing possibly is just that the amount of data on which ChatGPT was trained is just crazy big. It's pretty much just the entire internet, and then just filtered to limit the quality. Yeah, it's huge. And so because of that, the model has seen so much data that the more data you're going to see, this is a very basic principle in statistics, but the more data you're going to see, the better your model is going to be, essentially, right, at representing this data. And so I think that it's possible that models like ChatGPT, like language model, have just much larger data sets, and so are able to become just better model from an absolute sense than just like reinforcement learning model that may just maybe see a little bit less, samples in order to be trained, if that makes sense.
Yeah.
So obviously I find it fascinating that you mentioned intelligence, because yes, this is clearly like a form of intelligence, which is something also just interesting to reflect on, because what keeps confusing me is the fact that it's called generative modeling, because it seems like it's generating something bigger than what it is. So it seems like the output is bigger than the input, but as you said, the point is to replicate the input as best you can through the model. But anyways, I was just wondering, what do you actually what is your research then actually about? How do you use generative models? Is it anything to do with neuroscience, or is it focusing on the machine learning?
Yes, so those are all very good questions. I guess just to echo your remark on the fact that generative models are just trying to replicate the data. It's true, they're trying to replicate the data, but there is this concept of generalization that is baked into this model. This model, essentially a model that would just output, let's say you have n data points, right? 10 data points, for example, as input to train the model. A model that would just give you randomly one of the data points. When you ask it to generate some new data, one of the training data points at random is not going to be a good model, right? For example, if you give them images of dog, and the only thing that the models get you is an image of dog from the training set, you could argue that it doesn't learn anything, right? In a sense. So you want the model to somehow find out about regions of the space that are regions of high probability for images, for example, but that are not necessarily present in the input training data. Okay, and that's the beauty of statistical learning, is that it's actually possible to do that in the many samples limit. So assuming that your training set is growing ever growing, there is a chance that you are able to perfectly find all the regions that are likely to contain valid images of dogs and stuff like that, essentially. So yeah, it's just not about perfectly replicating the training set, it's about perfectly replicating the distribution underlying the training sets. It's a little subtlety, but I just wanted to discuss that. So yeah, I think so about my research, I think so this was generative model 10001, I think. And so in a sense, the problem of generative modeling is absolutely not solved. There are plenty of questions to ask, and I think maybe the kind of three main topics of I could break down, I guess, research in generative modeling into at least three main topics of interest. The first topic of interest is just training. How do you train generative models? For example, can you have theoretical guarantees for training generative models? So how easy is it to find the best model within a set of candidates? These are the first questions. The second question would be where to apply generative model, right? Like, can they be used, for example, in other places than just image or text generation? And the third question would be, if you are given a generative model, is your model good or not? Evaluation. So there is training, evaluation, and application. And this is a very arbitrary, I guess, like dichotomy of the field of generative modeling. And I'm sure I'm missing out about a lot of other subdivision, I guess, of this field. But those are at least three, I guess, valid ones. And I've tried to contribute to like each of the three. So my first, the thing I started working on was to kind of design way of training generative model where your data is lying on a very, very, very narrow region of the entire space. And that complicates things a lot. That is the reason behind the creation of specific generative model like generative adversarial networks that were models that were very big in like 5 years ago, and that are still actually very key component of new models like diffusion model. Like if you look, for example, at stable diffusion, there is kind of stable diffusion incorporates something that I would call a generator, for example. And generators are key component of GANs. Okay, so there are an entire class of models that are all models that are aiming at representing generative process where the data is contained on a very, very small region of the space. And fitting this model is extremely complex for many reasons. And I guess the topic I started my PhD on is how to fit those models. And so we proposed different goodness of fit criterions that would allow you to fit model in a better manner, fit this kind of model in a better manner, essentially. So that was one of the aspects of my research. But I then transitioned a little bit away from this and started looking at where was it possible, like where could we apply, such generative models. And one place in which people are not necessarily aware of, actually, I think, that you can apply this model is in science itself. So you can use this kind of model to somehow find out about answer key question in a specific domain. Because let's say, for example, you have a model of the brain, right, in a sense. Then this model of the brain can be queried in order to answer questions like, what is the most likely value, for example, of some synaptic weights in the brain that could have best replicated the following voltage traces that I'm seeing in a neuroscience recording. Okay, and that's something people have actually done in practice. Correct me if I'm wrong, but I think measuring synaptic weight and the intensity of synaptic connection is extremely complex. It's not something that is easily accessible, unlike, I guess, the activity of neurons. And so understanding the strengths of the connection between two neurons is complex and can precisely be solved using specific complicated queries from generative model, actually. In that context, the generative model is actually a bit less black boxy than what I've described so far, which is, you take a Bernoulli distribution or something like that. In that context, the generative model is actually, let's say, a noisy Hodgkin-Oxley model. This is, in a sense, a generative model, right? It's going to generate voltage traces for you, and it's parameterized by the membrane conductances and some other parameters, okay, and possibly some kind of noise intensity. And then, provided that you have seen some data, you can find out about the most likely value, for example, of these membrane conductances or of synaptic weights if you have multiple neurons that are interlinked together.
I was just going to ask, like, where the probability fits into the Hodgkin-Huxley model, because there isn't really like a probability aspect. It's just input output.
So typically you have to make it noisy. And then suddenly there is like induced probability distribution that arises from the fact that you make the entire model noisy. So let's say Hodgkin-Huxley model is a differential equation. You can like see it as just like iteratively updating, like, getting the new value of the voltage at a given time. And you could imagine that at each time you add a little bit of noise, a little bit of jitter to your model. And that makes, and that represents the fact that there is some, kind of like unknowns aspect of, like unknown activity in the brain that is going to impact the value of the potential of the membrane potential at each time. So there is indeed, we need indeed some kind of noise component that is not necessarily present in the original Hodgkin-Huxley model for like single neurons, So the third aspect that I've not touched upon yet is the aspect of model evaluation. And this itself, again, is a very wide domain and with like tons of different little branches. But one thing that I've recently focused on and that drives like a fair fraction of my research these days is the problem of uncertainty quantification. So or in a maybe in a slightly less terse formulation, the concept of reliability. So the general idea is that you can't expect a model to perfectly fit your data all the time. It's just a too hard question, right? So you could focus on finding out, for example, to evaluate your model, what's the difference between the kind of true data distribution or like whatever estimate you have of it and the model. And you might try to estimate that difference in a sense, and this will tell you how good the model is in an absolute sense. If the difference between the model and the true distribution is very high, even though your model is the best model among the class of candidates that you defined, it may be still not be super good. And finding out about this is very important. But there is another thing which may be very important, which is, okay, you can't expect, since you can't expect even your best model that you have in mind to be perfect, you could think about other axes than just perfectness in a sense to evaluate, and perfectness being the thing I was referring to right prior to that. And that thing I have in mind is reliability. And so reliability is in a sense relaxing the concept of being perfect to just the concept of being honest. So think about, for example, what's the difference in an exam? So in an exam, if you have a multiple choice question, you could have two kind of behaviors. One behavior is like on questions where you know the answer, put the right answer. So this, I guess, is normal. But then there are questions in which you don't really know the answer, right? And so then you could have two possibilities. The first possibility is just to kind of wing it and to just give an answer at random and be like, yeah, And if the teacher were to tell you, are you sure about it? Well, you're not going to tell them that, like, you said that at random. So you're like, yeah, I'm quite sure about it. Okay. But truth is you weren't. Yeah, you didn't know, and you just had, you thought that it would be a good idea to just try out one answer at random. Another possibility would just be to be honest and to not answer anything, which is often the case in multiple choice questionnaires that you are asked to fill during your education. And in that sense, you're being honest, right? You don't know the answer to the question, and you're signaling it by not answering anything. Now, the question is there a better behavior between the two? I won't delve too much into that, but I would say that my personal preference when facing someone is that person tells me whenever they don't know, instead of try to just like kind of fall their way into a specific answer. And that specific property of either model or individual can actually be relatively well formalized in the language of statistics. And better than that, it can actually be tested. And so the kind of, very recently, I've started focusing on whether or not, if you're giving me a model, whether or not I could tell you, okay, that model is honest. That model is not going to tell you that it knows something when it's actually uncertain of the answer. And reciprocally, when a model is very certain about the answer, it shouldn't tell you, well, I don't know that much. Okay. And you can formalize it by thinking about, when a model gives high confidence to an output, that you want that condition on the event that the model gives a very high confidence to an output, that the model makes very few mistakes, okay? That the model is correct a lot of the time. And on the opposite side, you want that when a model doesn't give any high confidence to any output, you will allow the model to make a lot of mistakes. And this, again, can be even more quantified, and you can design very robust tests to check whether or not this specific pattern of behavior manifests itself or not for a given model. And so, yeah, that's what I've been working on recently.
Yeah, that's really interesting. So I wanted to ask what advice you have for anyone that wants to get into the machine learning field. What are the biggest challenges and what are the fun parts?
I think this is very, very, very person specific. So I think, for example, it may be completely fair. And I think maybe the right thing to do is to think about impact first. Like maybe people are really passionate about things that have the highest impact. In that context, I would say you would need probably some amount of math background and stuff like that. But advancing the frontier of generative modeling is also just a lot of engineering. So, of course, I guess the natural trade-off would be, should you learn math or engineering? Well, I would say if you want to maximize impact, probably the best thing to do is to learn engineering, right? If you are more, I guess, like sensitive to like the beauty of like theoretical statistics, which is, part of my case. It's not to say that I don't care about impact, but I really enjoy in my daily life, like the fact of being constantly faced with math, because I think the structure in there is absolutely stunning. And so if that's really what drives you, I would suggest like math lectures, take stat lectures, learn about machine learning, and there are plenty of different materials that are great, from just like starting back to math undergrad to like reading textbooks to doing reading groups with other people in your field, like depending on how hard I guess you want to transition from whatever you're doing right now to machine learning, either part or full time. But yeah, I think there is this definitely machine learning is full of this interplay between mathematics and computer science. And the question of what emphasis to put on is driven both by impact, but also by just what's your personal taste and enjoy doing the more.
I wanted to ask, so with neuroscience, there's like quite a lot of gaps in the field. There's a lot that we know about the anatomy, about the firing rates of neurons, correlating with behavior, etc. But we still don't understand how the brain works. And I wanted to ask, in machine learning, what is the gap in knowledge? And if you think it's equivalent to the gap in knowledge in neuroscience? I know this is a difficult question because you're not a neuroscientist.
I think that's a great question. I think there are definitely lots of parallels to make between so the brain and large statistical model for language that are present in machine learning, because both of them are pretty much not still understood at all. And both of them are very complex. They incorporate like billions of degrees of freedom, being both, it's pretty much the same order of magnitude. If you look at like very large language model, the number of like parameters are on the order of 100 billion, which is pretty much the number of neurons in the brain. So they are at least of comparable scale in a very crude way of comparing models, or comparing systems, machine learning. So there is a gap in both domains. But one thing that we have in machine learning that we don't necessarily have in neuroscience are cheap recordings and almost unlimited recordings. And that, I think, the fact that combined with that, the capacity of this model, the gap between the capacity of both of these systems seem to reduce over time. I think it's reasonable to ask, should neuroscientists study transformers? Should neuroscientists study large language models? And maybe somehow large language model can be seen for neuroscientists as incubator that would allow them to better understand the brain. Or even now, should neuroscientists, like if you're a neuroscientist, you should even ask yourself, what is it that I like about the brain? Do I like studying a complex system? Or do I like really the biological aspect of it? And if your answer to the question is number one, then no, why not joining machine learning?
Recruiting people to the machine learning side. Okay, thank you. With that, I think we'll conclude today's episode. Thank you so much for joining us, Pierre. It's been very enlightening.
Thank you for having me.
Thank you so much for sharing all your knowledge on machine learning and generative models.
If you liked today's episode, please feel free to share it on your social media and check out our website, neuroversepod.com, for the resources of today's episode. Today's episode was made possible thanks to the support of the Sainsbury Wellcome Centre Public Engagement Fund. We would like to thank Sainsbury Wellcome Centre for the generous grant supporting science communication initiatives like these.